Okay, good afternoon, everyone. So we're going to get back to our discussion about gradient descent and optimization. So we spent a while understanding gradient descent, and we talked about first order approximation of functions using gradients. And so we're going to put all those ideas together today and finally develop our algorithm. So the first thing, however, is to sort of step back for a moment and reflect on what we're trying to do. So we are trying to minimize a function. So for example, let's look at this really simple scalar case where I have a single parameter. I'm trying to find the location of that parameter that minimizes this function. And as you can see over here, there looks to be a minimum right here, right? The function small and big. And so that's, and we also said that at that minimum, the gradient is 0. And so that has been our guiding wisdom to try to set the gradient of functions to 0 in order to minimize them. But when you step back and you look at this, you see the situation is not quite as simple as that because, for example, maybe this value over here is actually lower than this value. So that says that this whole idea of looking at the places where the gradient goes to 0, it could be that maybe the function has another minimum over here, right? So there's actually multiple places, or multiple minima where the gradient goes to 0. But then we also see that there's another place where the gradient goes to 0, which here is a maximum. So this thing about the gradient going to 0, we have to be a bit careful when we try to do this. We have to realize that yes, that's one way to find the solution we're looking for, but we might find, depending on how we do it, if we're not careful, we might find something else. Okay, so that's just sort of keep in mind. And so in general, when we talk about places where the gradients go to 0, they're called stationary points. So stationary point of a function is any input that makes the gradient of that function go to 0. So here we've uncovered in one dimension 2 types of stationary points. We have a maxima and a minima. But there's actually another case that can happen. We can have what are called saddle points. And saddle points, here's an example of a saddle point in 2 dimensions. So we're trying to optimize those parameters, and then this is the function. So at this point right here, the gradient also goes to 0. In both this direction, the slope is 0, and in this direction, the slope is 0. And in this case, what you can see is along one of the dimensions, this point looks like a minimum, but along the other one, it looks like a maximum. So it's sort of, it's in a special class called a saddle point. So this is something that we're usually in machine learning, we like to avoid these things because they're not where we want to be, but they can confuse some of these methods. There's more complicated saddle points like this one here, where, so when you look at this, basically the curvature in one direction is curving down, and here it's curving up. But in this case, at this saddle point, the curvature is actually 0, so it's even a little bit more complicated. So the point is that there are these cases where you have stationary points that are neither minima nor maxima, call them saddles. And we'll hope to avoid them, but it's just have to keep in mind. In some cases, we definitely know we can. In other cases, we'll have to be more careful. Okay, so with that in mind, here's the approach we're going to focus on. It's called gradient descent. This is the simplest version of the workhorse optimization approach used in machine learning. So our objective here is to find the minimizer of this function j. I've been using different names for this. I've been calling this a cost function in this unit. In previous units, we've called it the loss function. Sometimes people call it the objective, but it's the thing we want to minimize. And as we recognized, really all we can hope to do is find a local minimizer, meaning maybe there's a minimizer here, but as you can see, there's another minimizer here. So you would call each one of them a local minimizer. Like in this neighborhood, that's the minima. In this neighborhood, that's the minimum. So this is what we're going to just try to find a local minimizer. And another important thing is that we have been focusing on unconstrained optimization. So let me explain what I mean by that. So imagine that I have a quadratic. So we know that a quadratic, it has this one minima here, right? But now what if I tell you that actually we're only interested in finding, we're only allowed to look at parameters to the right of, maybe this is 0. So now, when you look at the new minima within our allowed set, we're constraining beta. Now the minima is here, right? Which is no longer at a point of 0 gradient. So this is another complication, but we're going to avoid this by assuming there are no such constraints. So we're doing unconstrained optimization, not this constrained optimization. I'll have more to say about constrained optimization in the next unit, but in this unit, we're focusing on unconstrained optimization. Okay, and another complication that I've mentioned a few times is we're focusing on zeroing the gradient. That means that the gradient must exist. If we have a function like that has a sharp edge where there is no gradient defined there, then we can't look for the gradient going to 0. That's not going to show us where the minimum is. So that's something else we have to worry about. So with all of these kind of qualifications, the gradient exists everywhere. The optimization is unconstrained. Here is the approach that we're going to use, algorithmic approach to find the minimum. So essentially, we're going to start with some initial guess. Often this is a randomly chosen guess. Perhaps maybe this is the guess we're starting with. These are the contours of the cost. We're trying to find the minimum, which is here. So this is our approach. From our initial guess, we keep iterating this step. So essentially this says at every iteration k, so in other words, k goes 0, 1, 2, 3, and so on. At every k, you take your previous guess and you subtract from it some number alpha k times the gradient evaluated at your previous guess. This alpha k is a small positive number. It's called the step size or the learning rate. It tells you how far you travel. The direction you're traveling in is the gradient, or negative gradient. So remember, the gradient is always pointing the most steep direction uphill. The negative gradient is always pointing in the most steep direction downhill. So this says, take steps in the steepest direction downhill, but don't go too far. Here's what happens if you go too far. Let's say you're here. This is the steepest direction downhill. What if I take a step all the way over here? Now I'm actually at a higher contour, at a worse place than when I started, right? So I've kind of overshot and I've gone way up the other side. I don't want to do that. From this direction, if I take a small enough step, then I know that I'll go downhill. Right? So that's the idea. And it has to be a positive step. If I take a negative step, then I go the wrong way. So this has to be positive, and it has to be small enough. And we'll get into those details. We'll prove it on the next slide, I think. So here's sort of what happens. So this is your first guess. You take a small step. That lands you here. Now this is your next guess. At this point, the gradient is actually now pointing in a different direction. Whenever you view these contours, remember that the gradient will be perpendicular to the contour. So here, the gradient is going this way. We're moving the negative gradient. That brings us here. Now, the gradient is a little bit tilted. So now we're going to move this way. And we're going to gradually move closer and closer and closer. And eventually, if we continue this procedure forever, we will eventually converge to that minimum. the steps are getting smaller and smaller. So why are they getting smaller and smaller? What do you think is causing them to get smaller and smaller? Can you hear? Yeah. So what's happening is that the steepness, the norm of the gradient, the steepness of the cost is getting smaller and smaller. It's getting flatter and flatter as you come towards the center. So even if you use the same step size at every iteration, this itself is shrinking. So we're just taking smaller and smaller steps. Okay, so that's, in words, the algorithm says take small downhill steps until you reach the bottom. So this is a very simple approach. You can write it in one equation with a couple terms. This is not, as we'll see, this is not going to be necessarily the fastest approach, but it's the approach on which all other fancier algorithms are based. They're just fancier versions of this idea. Question?
How does this algorithm avoid reaching a local minima instead of a global one?
Well, you're saying how does it get trapped in a local minima, not a global one? So let's look at this picture. So if I'm using gradient descent here, and I start here, let's say this is a lower value, right? This is what we call the global minima. This is a local one. So if I start here, then I'm going to get stuck here. I won't make it all the way there. On the other hand, if I start here, I'm going to converge here. So it all depends where we start. So basically, these are all called local minima. This one is also called a global minima because it's the best of the local minima. Does that make sense?
Yeah. So it can't avoid local minima?
Yeah, this algorithm, basically there's a basin of attraction around every one of the local minima, and if you start there, then that's the one it will converge to. Yeah. There's various ways to try to avoid that. We'll talk about those details in a few units when we talk about deep learning, because in that case it's really important to use those tricks. In this unit, all the cost functions, all the losses we've looked at so far have been convex. In this case, as we'll talk about it in maybe next time, it turns out that all the local minima are global minima. So we don't have this problem of converging to a bad one. It's just in the non-convex deep learning case, we'll have that issue. Okay. All right. That was a good question. Are there any other questions about gradient descent? Is this sort of making sense, like what it's doing? Yeah.
So the solution that we get, it may not be the best possible solution.
It's going to be locally the best solution, but in a global sense, it may not be the best. Any other? Yes.
Could you potentially add like constraints to make it skip past global minimum if you wanted to reach a global minimum?
There's all sorts of tricks you can play. I don't know if I call them constraints, but there's definitely lots and lots of tricks, and that's what non-convex optimization algorithms, they all have their own tricks. So yeah, we'll talk about some of those tricks in Unit 8 or 9 when we get into deep learning.
So can we choose the best start point?
Yeah. In some cases, if you know more about the loss function you're minimizing, you can somehow come up with a smart initialization that you know is maybe near the global minima, and then you combine that smart initialization with gradient descent, and you can get a good solution.
So there's some method that we can find that.
Yeah, for certain cost functions, there are some methods, but nothing universal.
And then how do we know when to stop the iterations?
That's a good question. So there's a few methods that are used, or maybe in combination they're used. So one thing you can do is you can keep track of the the height. And when you see that, when you see the difference in heights go under some threshold, you might say, I'm done, I'm not really making much progress. You can also do it with how much you move. You can say, like, this is the difference in the norm of the last and current omega or W vectors. In that case, that's not changing much anymore, so I'll stop. You can look at the norm of the gradient, too. That says, when it's shallow enough, I'll stop. You can look at some combination of all those things. Or you can just say, I'm going to run it for 1,000 iterations. And that's the simplest, and that's what we'll do in most cases. Okay, great questions. Any other questions? Okay, so let's try to prove to ourselves that this actually works, because it seems like it works, but how do we actually prove this? So what we can do is we can use some of the tools that we've developed until now. So we're going to start with the Taylor series expansion of our function at or around the old point in our gradient descent update, WK. And so for this, we're going to have J at WK, the constant term, plus the gradient of J at WK transpose times the difference between W and the reference. And then we're going to have a higher order, a big O that collects all the higher order terms. And this is going to be the difference between W and WK norm squared. And so here we're assuming we have a vector of parameters, not a matrix, not a scalar. Okay, so that's the Taylor series expansion that we've seen before. And so the next step is to evaluate this for the specific W that is the output of our gradient descent step. So we have, you can say this is like the input to that step, and this is the output to that step. And there's a nice thing, if you notice, like if you subtract, if you take this equation and you subtract WK from each side, well, actually, let's look at this equation first. Okay, so all we're going to do here is we're going to plug this in every time you see a W above, we plug in WK plus 1. So that means here you get a WK plus 1, here you get a WK plus 1, here's 1. And now you can see that there's this term here that's showing up. So actually, that term is something that we know because we're using gradient descent. So if we come up here, if I subtract WK from both sides of this equation, then I get that term, and it's exactly this, minus alpha k times the gradient. So minus alpha sub k times the gradient evaluated at WK. Sorry, I ran out of space there. Okay, so that means that we can plug this term into here and here. And when we do that, alpha k is just a scalar, so that comes out. We get minus alpha k times this gradient transpose times this. And then over here, this thing goes inside this norm. So the sign will not affect the size of the norm, and it's actually a norm squared. The alpha k, we can pull that out of that norm, and then it will get squared here. And then what's left in the norm is just the norm of the gradient. And actually over here, you might recognize this is also the norm of the gradient squared. So we actually have this norm of the gradient showing up a couple places. So to try to simplify things a little bit, we can take this big O term, and we can pull out the norm of the gradient. That just scales everything. And then what we're left with inside the big O term is this thing on the order of alpha k squared. And so this is just saying that alpha k squared is bounded above by some constant. c times alpha k squared. But we don't know what that constant is. We'll just call it c. So this is essentially what it's telling us. So this is what we have. This is really all we can say with certainty is that the cost at the end of the gradient descent step is the cost at the beginning modified by two different terms. So our goal is that the cost after we take the step is smaller, right? We want the cost to decrease going from here to here. So will this term help it decrease, or will it hurt it from decreasing? Help it. Okay, so for those who said help it, how do you know it's going to help it?
Norm is always non-negative.
The norm is non-negative, and what about alpha k? Positive, right? So these two together can never be negative, and so they're positive or at most zero, or at least zero. So this will help us decrease the cost. What about this? Does this help us or hurt us? Hurts us, right? Because these things are positive, or in the best case zero, but they could be positive. So this is sort of this reflects the difficulty in choosing the step size. If you choose the step size really small, as we saw in this picture, you can make progress. If you choose it too large, you can actually make things worse. And that's sort of reflected here. So we don't know what C is, but we know it's some number, right? So what's the value of alpha k that balances these two terms here? What value of alpha k will make them equal? 1 over c, right? Because this gets to be 1 over c, and then this also gets to be 1 over c when alpha is 1 over c. So when alpha is 1 over c, that's the exact borderline between, helping and hurting us. What about when alpha is less than 1 over c? Which term will dominate? When alpha gets really small, this one, right? Because when alpha is really small, this is even smaller. So this ends up being the more important term. So by choosing alpha smaller than 1 over c, we're guaranteed to make progress, or at least to never go in the wrong direction. And this is true no matter what c is. We don't know what c is, but we know there exists some step size, 1 over c. And if you make a step smaller than that, you're good. You will make progress on that iteration. Okay. So this is the idea. This is sort of the proof that this works. Now, it's a trickier thing in practice to know what that value is. So we're going to come back to this, and we'll derive a more sophisticated algorithm that tries to always make progress, even though C is unknown. But we'll do that in a little bit. We have a few more things to talk about just for this basic version. Okay, are there any questions on our analysis here? Is this making sense? Okay. Good. So, all right, so we talked about this a little bit already. The idea that here's the global minimum, local minima. You just have the same for maxima, global maxima, local maxima, and so on. All we can say about this method we've developed is that for small enough step size, we're guaranteed to converge to a local minimum, maybe not the global one. But the saving grace is for a convex function, any local minima is a global minima, and we will define convexity a little bit later and get into those details a little bit later. So there is hope that actually we're not doing this. We're doing this for good reason. There's a lot of convex functions. We've actually been working only with convex functions. And so this approach will work for us, especially for the cross entropy loss, which is really the kind of inspiration for this for this unit. This is what our demo is based on. We're just trying to minimize this. So this is the thing that we derived in the last unit, and it's a little bit complicated in the sense that we have this term, which has like logs and exponentials, that's written in terms of these zi's. The thing we're minimizing over w is used to create the zi's. So particular zi is 1, and then the xi transpose vector, that is a row vector times w, which is this column vector. So it's a little bit complicated because there's sort of two stages, two parts to this loss function. So we're going to exploit this to derive the gradient. And this is going to be a super important technique as we go through the course, because we're going to be dealing with more and more complicated functions that are the cascades of many, many, many different stages of things. And we need a tractable way to approach these problems. And the way we're going to do it is using something called the multivariable chain rule. So, so to set this up, if you think about this overall loss here, we can think about it as a composition of two functions. A composition is just where you take the output of one function and you plug it into another one. So the first function is one that takes us from the parameter w, the parameter vector w, to a vector of all the zi's. Okay, so that's this, and we've seen this before. So we know that z, the whole vector of all these zi's, is our A matrix times our W vector. Our A matrix is something we saw back in Unit 2. A is the X feature, so the feature 1 has these guys as the rows, and then it has the column of 1s here. So you can think of that as the first step of processing in this function. And once you know the zi's, then you can plug them into this. And so this is a function that also has an interesting structure. It's called separable, because when you take this zi vector, this cost function says you take each individual term out of this and you work on that directly and then sum those guys. So in other words, there's no interactions between the different z terms. It's just a sum of functions operating individually on the z terms. So these are two types of structure that show up a lot in many different problems. And we can leverage both of these structures because when you look at them on their own, they're actually pretty easy to deal with. When you put them together, that's when things get messy. So the way that we're going to, and here's how we can write everything together. If you like, you can say that j is a function of w, is z is a function of w, and then the z is put into this f function here. Okay, so the way that we handle this is the multivariable chain rule, which is something I'm sure you all saw a long time ago. Maybe you haven't seen it lately, but this is a super important thing that we're going to start using a lot. And it's relatively easy to remember this. Whenever you have a cascade like this, and you want to take the derivative of something on the input here, you do dj dwj is a sum over all the intermediate variables inside here, z. So sum over these indices I of df dzi times dzi dwj. Okay, so one way you can think about this is that there's many ways for the jth term in w to affect our cost. The jth term here can affect the first z, which will then affect the cost, or it can affect the second z, or the third z, and so on. And that's what's showing here. It's saying this is how much, this measures how much wj affects zi, and then you have to look at how much f is affected by each zi, and then you sum over all the i's. Okay, so that's just, it's exploiting the fact that there's many paths from each w to this f or to the final j. Okay, so this is going to be how we approach all these problems. And so now, in terms of the derivation, we just have to figure out the forms of these two things, and then we just plug it in and go. Okay. So any questions on the overall approach, the composition approach? Is it clear how we've looked at this as cascade of two things, and now we have them both defined. Here's our function fi of zi, and then here's our function z of w. Yeah.
Is there any reason why we can't just use the ZI terms to cancel each other out?
No, what do you mean by cancel each other out?
I mean, wasn't the
Oh, I see. Maybe it's a notational thing, but it's like, think of this as, this is like a function, df dzi, right? And this is another function. Or, I don't know if that answers the question, but I mean, in some sense, if you canceled these out, then you'd kind of be back to this df dwj, which is what we have on the left. So it's like we're kind of purposely expanding this to understand the different pieces and how they fit together. Okay, so let's look at this. What is df dzi? So here's okay, so I guess, yeah, so let's look at this. So this is the big F, which is the sum of many little f's. So when I look at df dzi, the first thing is we can see, because of the separability property, the only I here I need to worry about is the same I of z. In other words, maybe in case that was confusing, we could put primes here to make sure that those i's are different than this I. And then when you say, look at the derivative of this with respect to zi, there's only one I prime term that matters, and it's when I prime equals this I. And at that point, you can just focus on this alone. Okay, so at that point, we just need to do d this dzi. Okay, so how do we do that? So, all right, so let me get back to my attendance here. So is Dion Chen here? Okay, yeah. So what do you think? How do we do that?
1 over 1 plus EZI and minus YI.
Okay. Okay, we forgot.
Oh, forget the EZI.
Yeah.
Multiply here.
Okay. Okay. So let's do this step by step. So whenever you differentiate natural log, you get 1 over the argument, right? So when we do this, we get 1 over this, but then by the chain rule, we have to take the derivative of what's inside with respect to zi. So we have to do e to the power zi, differentiate, with respect to zi of that, and then that gives us the same thing. That's the first term, and then the second term, differentiate this with respect to zi, we just get minus yi. Okay, so is everybody good with this? Okay, we can, let's say, simplify it too. Is there a way we can simplify this a bit? We saw this before. What we can do is we can e the minus zi plus 1, right? Because I can multiply top and bottom by e to the minus zi, and that will cancel this and turn the denominator to that. Okay, so this is a little bit nicer because zi only appears once, here it appears twice. Okay, everybody good with this? All right, what about this dzi dwj? So we have to look at this equation here. So if we're focusing on zi, we're looking at one particular element in that column vector, which means we're going to be looking at one particular row of A. And then we're also looking only at Wj. And Wj is going to be one particular element here, which will look at the corresponding column there. Okay, so at the end of the day, hopefully you can see that this involves only one term in this A matrix. So what is it? What is d zi wj? A sub ij. Okay, so like that. Okay, so so those are the ingredients of the multivariate chain rule, and so that's, you know, most of the work is done. The thing to do next is try to come up with an efficient implementation of this in Python where we're not repeating a lot of unnecessary steps. Any questions on these derivations? Okay, so let's move to the next page. So as I mentioned once before, typically when we compute the gradient, we also want to compute the cost too. And now we can understand a little bit more why that's useful, because as we're, you know, taking our gradient steps and computing the gradient over and over, we want to keep track of the value of the cost to see, is it still decreasing? Has it saturated? You know, what's going on? So we're going to compute both together. Compute both the cost and its gradient. And the way that we're going to do this, the way that the computations tend to be organized, is what's called the forward pass, which is something where you're computing this, and then the backward pass, which is where you're computing gradients. So forward pass does not involve any gradients. Backward pass involves these gradients. The forward pass, essentially when you compute this, you compute things like z's, which you need to actually evaluate your gradients, right? So the forward pass sort of sets everything up. Okay, so the first thing we're going to compute are a vector of z's. And that's easy. We know that given a w vector, we just take a times w and get our z vector. Second, we want to evaluate our cost. Our cost, if you remember, you can write it as f of z or as the sum over I, fi zi. So we just need to evaluate these individual guys. And we derived on the last page that they look like this. But if you notice, this has a 1 plus zi term, and later on we're going to have to do this. Maybe we can do a little bit of massaging of this so that it looks like this, and then compute that one thing once and not have to compute similar things twice. So that's what we're going to do. So I'm going to do something a little tricky here. I'm going to write this as this. Let me explain what's going on. So when you look at this part here is the same as this, right? Because when you put a negative in front of a log, that's like putting its argument in, inverting its argument. But then there's this new term which looks like this. So altogether, that is minus zi. To compensate for inserting a minus zi there, I'm going to insert a zi here, so that those two things will cancel. And then the only term remaining is here. And so hopefully you can agree that these are equal. The reason I made this is because we know that we can then simplify this down to this, which is exactly the thing we need to compute over here. So that means we can compute it once, and then we will we'll get to use it twice. Okay, so that's the first thing. We'll go through the code in just a moment. The second thing is we want to compute. We want to use the multivariable chain rule like this. So this was from the previous page. This was the expression. This is the gradient or the derivative with respect to wj. And we derived this equals this. And from above, we know that this part is, let's see, Did we get that from above? No, we derived this on the previous page. That's what we derived over here. Okay. So, so we have most of the ingredients, but the thing is, we don't want to use for loops if we can avoid them. For loops are incredibly slow. So these are the components of the gradient vector that we eventually want to compute. So in particular, the gradient vector is just a stack of these guys. And we know to construct each one of these guys, we have something like this. These are the components of another vector, which I'll call gradient of f. Gradient of f is a vector of all of these terms, here. So let's see how we can use both of those vectors together. Okay, so to start, from this equation up here, you can see that for any j, it's going to be this vector transposed times this vector with the j we're fixed. So for example, let's say that j is 0, this becomes 0. And now to compute that scalar, we're going to have, let's say, a row vector of these terms times a row vector of these terms. So in other words, we get this. So here's the 0, here's all these terms, here's all of these terms, and here's the sum over I. Another way to see this is it's like this times this gives you this. So here we're expanding out the different terms, aij, and here j is always 0. Now if you move to the next j, if you put in like a 1, then this becomes a 1, and it has the same form. So that's going to be the next row here, and the same vector of here, of those guys, and so on. And you can do this all the way down to the last one, which is WD. You get this, which gives you this set of A values and the same gradient vector. And now if you step back and say, oh, okay, this is just the A matrix transposed, and this is just that gradient vector, the df dz vector. So now we have things written finally in a very compact way. We have this, and we have, let's see, the gradient vector, yeah, so these are the elements of it. These are the elements. And we're pretty much ready to go. So let's look at what the costs or the code looks like. So the first thing we need to do is we need to build our A matrix. We're going to be given the features in the X matrix and the targets in the Y. And so we essentially need to build the A matrix by creating a vector of 1s and then stacking that next to our X matrix. This gives us our A matrix. Now that I have that matrix built, I can compute Z by just doing A dot W. Can also compute this term, which I'm going to use a couple times. I'll call that PY. That is computed here. This is using Python broadcasting because this is a vector. And finally, now that I have those PYs calculated, I can compute this. So this is going to be, I'm going to sum this over all the I terms. And the first one is going to be 1 minus y times z, that's this, and minus log py, that's this. Okay, so basically that's how we can get our cost, j, and now our gradient, because we did this hard work before, the first thing we can do is, let's see, df dz, so that is this term. You can see that that's py minus y, like this. And then we have the gradient is this vector, or this matrix, A transpose dot this df dz. So everything here is computed in just a few lines very efficiently, and then we return j and its gradient. Okay, so here we try to be efficient, and no for loops, nothing like that. So as you can see, when you implement some of this stuff, you have to think carefully about how to construct matrices and vectors, and this is, yeah, the linear algebra becomes more sophisticated here. You'll see the lab for Unit 6 has quite a lot of this kind of stuff in it. All right, are there any questions on anything in this page? Okay, all the steps are making sense? Okay, so now we have a function. This is the same function from the previous page. We've built this one where we give it an x and a y, and the current w, and it computes the cost and the gradient to use in the next gradient descent step. So now when we're iterating this, often we don't want to often we want to hide the dependence of x and y, because x and y are common every time we're running this. We have the same x and y. So we want to think about this as just as a function of w. What we can do is we can use what's called a lambda function in PyTorch. A lambda function is just like a wrapper that essentially fixes the values of some parameters and leaves other ones free. So this is how it looks like here. So it says, essentially, let's make a function of w alone, and this is going to be the function. So here is how we're going to make it. We're going to take our j eval. We're going to plug in fixed values of our training labels and targets, but we're going to let this w be free. So now I've created a new function that is only a function of w. You may have seen this in MATLAB. In MATLAB, they're called anonymous functions. They work exactly the same way. It's just the syntax is a little different. Okay, so now that we've created this j-eval function, if you want to evaluate the cost and gradient at a given point, omega 0, this is how you do it. You just do j-eval w0. Okay, so really not much. It's just sort of we're wrapping this in a way just to make it a function of one variable. And this, once in a while, this is a useful thing to do. Okay, so that's lambda functions. Now there is something that's a bit inefficient about this approach, which is the fact that every time we are computing a cost and gradient, we're recreating this whole A matrix. That's sort of inefficient. Maybe we can just do this once at the beginning and then not do it every time. So to do that, there's a more powerful way of approaching things, which is to create what's called a Python class. This is an instance of object-oriented programming. And so here you can see we're setting up a class with this name. And this class must have what's called a constructor. And a constructor is the thing that is run when you instantiate the class. So our class is called logistic fun here. And when we call it first, what we're going to do is we're going to call it with the training data. And it's going to essentially, when we call it, it's going to run this piece of code, which, as you can see, it takes in x and y, and it stores y as an internal variable. So when you see self.y, that means it's remembering y, and it's now that is sort of loaded within this class, you can access it through any other function in the class. So we're going to create this other function, j-eval, and it's going to have access to this self thing, which means it's going to have access to y because we sort of stored y internally. Then we make this temporary variable n, which is just the number of training samples. And notice we're not storing this in self. This is just a temporary thing. We don't really need to save it. We're just using this to make the ones vector the right length. We're making the A matrix, but we are going to store the A matrix as an internal variable. So once we do this once at the beginning, now we've stored y and a. And now when we compute our cost and gradient, what we're going to do is we're going to do log fun.jeval. So that's going to call this function. And that function takes in whatever W. And this contains essentially the same things that we had over here, just copied and pasted them. But notice that they have access to self.a, self.y, and so on, self.a again here. Okay, so now when we do this, we only make the A matrix once. That saves computations, and this is what we do. We just execute the minimum code we need for every step. Okay, so any questions on that? Okay, so you've seen this stuff happen like every time you set up your linear regression object in Python, in scikit-learn, that's exactly what it's doing. It has some initialization code, a constructor. You know, you give it whatever you need for that, and then you call things like linreg.fit, you know, and then it calls some other function that has access to the training data that you loaded previously. So this is just following exactly what you've been using, but now you get to see the internal guts of how that's done. Okay. Now, as you can see, this is, you know, we had to do a lot of derivations here for all this stuff. It's very easy to make a mistake, either in the derivation or in the coding of the gradients. It's almost guaranteed the first time you try this, there will be some mistake. You will have some debugging to do. To check to see if there's a mistake, there's a nice trick, which is this. So you basically pick 2 points, W0 and W1, that are very close together. Just choose them randomly. And then check that this equation holds true. So where is this coming from? This is coming from our first order approximation. So I took the first order approximation, and all I did is I subtracted this from both sides, right? And we know that this holds anytime W1 is close to W0. So what you do is you enforce, you know, them random but close together, and then you just make sure this is true. If you find that this is not approximately equal to this, you know you made a mistake, you got to go and debug it. And don't do anything until you get this satisfied. So here's how we do it. First, we extract the dimension that we need, which is just the number of features. Then let's make a random W0 vector. So this is numpy.random. Rand_n, this is a normal distributed or Gaussian, 0 mean, unit variance. So this is just a random vector of weights. Now we're going to make W1 close to this. So we're going to have another NP random rand_n, but we're going to multiply it by a very small number, in this case 1e minus 6. So these guys are very close together, but both random. And then we're going to compute these values here, the J and the gradient at W0, and then we're going to compute J at W1. Well, of course, we also get the gradient. We won't use it. And now we can just essentially compute this. This is our predicted difference between J1 and J0. And then let's also print out the actual difference between J1 and J0. And you can see up to 5 decimal or 5 digits of accuracy, they're the same. If you go deep enough, you will see that eventually they differ because this is only an approximation. Okay, but because we chose these points pretty close together, they're going to be accurate to, you know, roughly the same number of digits that we chose there. So now that we see that things are in fact agreeing, it seems like our gradient really is implemented correctly, derived and implemented correctly, we can move on. All right, so any questions on this little trick? Okay, so we're almost done. So now we have everything we need to basically implement gradient descent. So this is just, here we have a for loop that iterates just over integers. Nit is just the number of iterations we're going to run. And what we do at every iteration is really just 2 things. Take the current W vector, we compute the cost and gradient, and then this is our gradient descent step. We're going to overwrite W0 by the previous one minus the learning rate. This is what we called alpha before. times the gradient we computed here. And so this is really all you do. You just iterate this over and over. But to keep track of what's happening, we're going to remember the cost and the parameter vectors. We're going to make this history object, and we're going to append to the end, which is going to we'll have like a list that's going to grow longer and longer the more iterations we run. And then to export it, we're going to convert that list to NumPy arrays and return the final W vector, the final cost, as well as our history. So it's as simple as that to program it. And now we can put everything together. Let's initialize somewhere. We're just going to initialize randomly. We're going to choose 2,000 iterations, a learning rate of 1e minus 4, and then now we're going to run our simple gradient descent and plot what happens. This is the loss over iterations. I'm plotting iterations on a log scale. So this is 1, 10, 100, 1,000. If you don't do that, it looks very boring. It looks kind of like that. But if you plot it on a log scale, you can really see better how things are decaying. And what we see overall is that even after 1,000 or actually 2,000 iterations, we're not done. It's still decreasing. The test accuracy is actually not that great yet. We can see essentially that, it seems like it's working. It's just really slow. And so what you might then do is you might say, okay, what about this learning rate? Was that a good value? So let's try different learning rates. And we'll plot the loss versus iterations for different learning rates. And this is, I think the blue one, no, the orange one is from the previous page. If we make the learning rate even smaller, then not surprisingly, it converges even more slowly. If we make the learning rate a factor of 10 larger, it does converge quicker, but you see that it starts to be a little bit inconsistent. What's happening is we're overshooting. We keep, overshooting. Although, overall, it seems to be working okay. You might say, well, that's great. Maybe I can make it even faster, so I'll make it twice as big. And now you can see it starts to go kind of crazy. And it's overshooting so much, it's not really converging. It just keeps overshooting over and over again. So overall, what we see here is that learning rate really does matter. If we kind of tweak things, we can find a good learning rate. But in doing this is quite expensive. We've had to do a bunch of manual experiments. We've had to run now 4 times the number of iterations of a single run. We had to be smart in our guesses and all that. And so all this motivates, like, can we somehow automate the process of choosing this learning rate? And that's what we'll talk about next time. But now we have the basic gradient descent algorithm. We know a little bit how it works. We know how to code it. So, all right. See you guys on Wednesday.